Good morning. In this talk, I will present some strategies to compute efficiently some sequence of linear systems associated with the neutron diffusion equation. To explain this process, I have divided the talk in the following part. First, I will present the neutron diffusion equation. Then, I will briefly describe the updated preconditioner. Then, I will explain how these updated preconditioners are applied to the sequence of linear systems. The numerical result will test the performance of the methodology. And finally, the talk ends with the main conclusion of this work. Here we have a scheme of a nuclear power plant where we can differentiate two types of processes. First, the thermohydraulics that study and simulate the water and the steam water that move the turbine, and also the water that refrigerates the reactor. In the other way, we can study the fission process that appears inside the reactor core. We are interested in this neutronic part, and obviously to know and predict efficiently this behavior is very important for the design and the safety of a nuclear power plant. Inside the reactor core, the time evolution of the neutron depends on the fission process and the interaction between them, and this behavior can be modeled by the neutron transport equation. This equation, to simulate this equation for a realistic nuclear reactor core, is very difficult, even though supercomputers or numerical methods are used. So we need to use other approximation, and in this work we have used the neutron diffusion equation. To make a spatial discretization of this equation, we have applied a Galerkin finite element method with Lagrange polynomial to obtain a semi-described system of differential equation of this time, where these matrices are the discrete version of the continuous operators of the equation that contain the materials and the cross-section that are dependent of the reactor. And here we have the flux of the neutron flux. To implement the finite element method, we have used the DIL2 library. This system of differential equation for a realistic nuclear reactor is stiff, so we need to use or is convenient to use implicit scheme to make the time discretization. In this work, the time domain is divided into several time steps, and where we apply a discretization of first order, we obtain that to approximate the flux in the time n+1, we need to solve this linear system where the matrices are given by this expression and the neutron precursors are updating by using this expression. So the objective of this work is to propose a methodology to integrate efficiently or to compute efficiently this linear system. Then we start with an initial linear system of this form, where A is a general non-singular matrix. In this type of computation, this A will be large, of order 7,000 millions, non-symmetric and sparse. And we want to obtain the neutron flux that in this case we denote with X. For this type of linear system, we apply Krylov method, and the aim of this part is to improve the convergence of the Krylov method. And in this work, we have used the GMRS method. This method, the convergence of this method depend of the condition number of the matrix, and to improve the convergence, we define a equivalent problem, precondition problem, to obtain that the matrix of this system PA, the smaller eigenvalues will be larger than the smaller eigenvalues of A, so the condition number of this problem of this matrix will be larger, so the Krylov method applied to this type of problem has a better convergence. Usually this P approximate inverse of the matrix, and in this case, the split are constructed by initial preconditioner plus a correction. First, we will talk about two preconditioner. They were introduced by Freytag in 2006 in the application of iterative eigensolver, and in this case, we use two iterative linear systems. So, with the previous definition of the previous frame, and if we select a matrix with 4-column rank, a tune precondition is defined as a matrix P that satisfies this property. We can observe that this S will be a matrix where in these columns are the eigenvectors of this P associated with the eigenvalue 1. So to construct this tune preconditioner, we can use the Good-Abad-Broiden that are derived from the quasi-static Newton method from the numerical optimization. If we consider the problem F like this numerical method approximates to the inverse of the Jacobian, that in this case will be an approximation of the inverse of A. So if we select S of 4 rank K, the Bad-Broiden are obtained like this, or if we apply the Good-Broiden algorithm, we obtain that the preconditioner are obtained by this computation. Both preconditioner, the Bad and the Good-Broiden, are obtained from an initial preconditioner, and they satisfy the tune property. Other type of preconditioner are the spectral preconditioner, that if we suppose that the matrix P0A is diagonalizable, such that we have this decomposition, and let S a matrix that does this AC has 4 rank, a left spectral preconditioner is defined at this type of matrix with this V epsilon denote the eigenvector that contain the associated with the smallest eigenvalues. So if we define this spectral preconditioning, there is a theorem that states that the matrix PA has the same eigenvectors of B as the matrix P0A, but the eigenvalues of the smaller eigenvalues are increased in one value, this value. So now we are going to show how can apply the previous update in preconditioner for a sequence of linear system. So suppose that we have a sequence of linear system where the matrix, the independent term and obviously the solution are changed. So to apply the previous preconditioner, we maintain the same initial preconditioner, and also we change the matrices and the vector columns of the matrix S in each case. So to select the matrix S at each time step, the theory states that the best option is to use the eigenvector associated with the AP0 or AP0 associated with the smallest eigenvalues. However, this computation at each time step is very, very expensive, and we use array vectors associated with both matrices, where Q is a basis that is obtained from to the Gimeris process or from the previous solution, where a orthonormalization process is applied to the previous solution. Now we are going to test the methodology in some nuclear benchmark. First, we use a small reactor to test the selection of S. In particular, we test the matrix to compute the eigenvector, the type of basis, and the rank of the correction, and then we compare the different type of updated preconditioner, and then we use a large benchmark problem to test the type of preconditioner, but also test a matrix-free implementation of this preconditioner. So here we have a three-dimensional Lang-Input reactor where the transient appears when the control roots are moved. This reactor is composed of more than 1000 cells, has two energy groups, and we apply a finite element method with degree 3 to obtain a problem size of near of 17,000 of degree of freedom. The transient is followed during 10 seconds, and if we select a time step of 1 second, we obtain 10 linear systems that are marked in this graphic, and the computation for this reactor is made in MATLAB. So to test the selection of the eigenvector of S, we select the first linear system, and the P0 will be the ILU of this is 0. And in this table, we can show the number of iterations of the GMRS if we don't use any update to the preconditioner. So the number of iterations is 44. And here we have the number of corrections if we apply the byproduct, good product, and the spectral are obtained from the eigenvectors of P0, A, P0, and A. The optimal is to use the first and the second type, but in the practice we can observe that if we use the eigenvector of A, good results are obtained, and we remove the necessity to use this process. Then we are going to test the type of selection on X, because the S can be obtained from the eigenvectors that are the theory that are the optimal. Then we can use from the read vector from the GMRS, and then from the read from the previous solution. For the bad Brownian and good Brownian, we can observe as the previous solution are obtained good result, even though are not very linear. It depends on the transient. And in the case of the special spectral preconditioner, the optimal is to use the eigenvector, but in this case also the solution of the GMRS in the decomposition are also a good approximation. In all cases, the previous approximation improved the result of not use an update. Here we have tested the rank of the vector, and here in all cases we can observe as a chunk rank approximation around enough to obtain good result. And if we use 5 rank process, we can observe similar number of iterations that in the 10 rank, and also will be more cheaper. So 5 rank is more recommendable. And if we compare the number of iterations for all type of update preconditioner to compute the sequence of linear system, and we select the rate vectors of A and 5 rank correction, and we use as initial preconditioner the ILU of A0, we observe that the good at the bad Brownian methodology with the previous solution, we obtain the better result in the number of iterations. So to test a most realistic problem, we have also used a large benchmark reactor that the problem has more than 1 million of degree of freedoms. Transient is followed during 4 seconds, and in this case the time step is 0.0 seconds, so we have 400 of linear system, and now the computations are made with C++. So here we have, if we use the P0 with the block-Gauss-Seidel methodology, and the updated precondition only have used the good Brownian. For the rate vector of S, we have used S from the previous solution and 5 rank correction. If we compare the number of iterations, we observe a reduction not very high in this part, yes, between use the same P0 of if we use a good Brownian that are updated, and the similar behavior are observed in the CPU times. in the total CPU time with the fixed P0, the total is 20 hours, and this is a small decrease of the time if we use update preconditioner. And now we are going to test a matrix-free implementation. To apply a matrix-free implementation, we need to use an initial preconditioner that cannot be ILU, so we have to use the Chebyshev polynomial. And in this case, the number of iterations are very reduced, and also the CPU time. If we compute the total CPU time, we can observe that if we maintain fixed the preconditioner, the times are 20 hours, but if we use the updated preconditioner, the time is reduced to a half. And if we compare with the previous case, we can observe that also the time is reduced to the half, and we can use any memory for assembly the matrix. So the conclusion of these works are: we have studied updated preconditioner to accelerate the computational integration of the time-dependent neutron diffusion equation. Tune preconditioner as bad and good Freudian are better option than the spectral. The selection of the basis from the previous solution is an efficient strategy. And the updated preconditioner had a matrix-free implementation that reduced the CPU time, memory, and also the times. To the end, only to add that this methodology has been incorporated to the open source C++ neutronic code FEMFusion. Thank you for your attention.